Hi, I'm Laurent Christophe, and this is my presentation for my PhD on provenance-aware dynamic analysis for JavaScript. I will start with a roadmap of this presentation. First, I will briefly introduce the background of my work. Then I'll move to the three main parts of this dissertation. The first part is about dealing with non-essential syntactic complexity. It is the most technical part of my research because it has to deal with a lot of corner cases. The second part is about tracking the provenance of runtime values. It is the more conceptual part of my research. And the final part is about orchestrating analysis for distributed applications. This part of my research is more experimental and has scaling issues. Finally, I will conclude this presentation with a technical overview and a summary. Onto the background. Here, I will introduce dynamic program analysis and code instrumentation. First of all, let's briefly define dynamic program analysis. In general, program analysis refers to the study of the behavior of programs. The classical approach is to model such behavior as a state transition system. To model the observable behavior of programs, we annotate transitions with actions. The fundamental limitation of program analysis is that the behavior of programs can be infinite or at the very least subject to combinatorial explosion. In my dissertation, I focus on dynamic program analysis, where only a finite execution path of the program is being studied. Compared to static approaches, dynamic analysis offers a precise but a partial view of the behavior of programs. During my PhD, I made an extensive survey of the state of the art, and I came up with a classification based on information needs. The easiest analysis to implement are the one that only needs the external behavior of programs, and this roughly corresponds to testing. More advanced analysis require accessing information private to the execution. This requires instrumentation to make this information available to the analysis. Simple extraction can directly derive the private information from the current state. I qualify this information as being intrinsic to the execution. More advanced extraction requires history to derive the private information. I qualify this information as being extrinsic to the execution. In my PhD, I focus on providing data provenance, which is extrinsic. I will revisit this analysis that I call Provenance-Aware in the second part of this presentation. My framework is based on source instrumentation. That is, the source code is transformed by inserting analysis logic. Consider the baseline execution of this program. For the input 9, it outputs 3. Code instrumentation can help understand what is this function f. Rather than executing the original code, the interpreter now executes the instrumented version. In this case, the instrumentation traces the name of the function f, which is normally private to the execution. And this instrumentation is transparent because it does not modify the baseline execution. Compared to other approaches, source code instrumentation has important advantages. First, it is portable and independent from any given interpreter. Second, it is generic and applicable to a wide range of analysis. And third, it extracts information that is adjacent to the source. This helps developers to interpret the results of the analysis. The main drawback is that implementing this analysis is complex and requires a lot of manual efforts. My dissertation aims to simplify the implementation of this analysis while protecting the strength of source instrumentation. So I have introduced dynamic analysis and the need for transparent instrumentation. And I have stated that my framework relies on source instrumentation. I can now move to the first part of my dissertation, which is dealing with the non-essential syntactic complexity of the source language. I choose JavaScript to illustrate my approach. First, because JavaScript is extremely popular, but the most important reason has to do with its history. Note the abbreviation ES, which stands for ECMAScript. It is used in the specification as a synonym for JavaScript for copyright reasons. JavaScript was introduced in 1997. This version was minimal and took inspiration from Scheme and the Lambda calculus. But JavaScript is very much alive and became increasingly more complex over the years. And this complexity is never going to go away because of backward compatibility. The goal of this part of my research is to enable analysis to focus on the so-called good parts of JavaScript while remaining able to analyze the full range of JavaScript programs. Here is a standard JavaScript instrumentation pipeline. The instrumentation is implemented by the user and manipulates source code as a tree structure. The de facto standard for JavaScript syntax tree is called ES3, which stands for ECMAScript 3. The issue with this instrumentation pipeline is that the user has to deal with the entire syntactic complexity of JavaScript. To solve this issue, we propose a detour in the instrumentation pipeline. Rather than instrumenting JavaScript, we propose to instrument a minimal variant instead. The research question of this first part is about defining this intermediate representation to alleviate minimal effort while preserving the strength of source instrumentation. My minimal variant of JavaScript is named AranLang. When I designed this language, I followed three main objectives. Minimalism is the original motivation for introducing the variant. As it becomes simpler, it facilitates instrumentation, which simplifies the use of the analysis framework. Coverage evaluates how much of the source semantics can be expressed in the variant. Coverage is necessary to protect the transparency of the framework. And proximity is how much the Transpiling program resembles its original version. Proximity is necessary to protect the source adjacency of the framework. At one extreme, we have JavaScript itself. By definition, it has a perfect coverage and proximity. At the other extreme, we have low-level languages, such as WebAssembly. They are minimal and capable of representing JavaScript semantics. However, at the cost of heavy transpilation expansion, which means that we are no longer providing source-adjacent information to the analysis and the user. AranLang strikes a delicate balance between those three contradicting objectives. It sacrifices very little coverage, and it is significantly simpler than JavaScript. It requires only reasonable transpilation expansion. Here is the complete syntax of AranLang. As you can see, it is much more complex than lambda calculus. However, it is much simpler than JavaScript. Let me provide one concrete example. In JavaScript, accessing a variable is dynamic, not atomic, and unsafe. Dynamic because the environment can contain dynamic frames. Not atomic because looking up properties in these dynamic frames can trigger arbitrary code. And unsafe because variables may be missing or in the temporal dead zone. These features makes it hard to reason about the environment, and they all have been removed from AranLang, which means that in AranLang, the environment is entirely lexical and safe to access. To make this high-level overview of AranLang more concrete, I'm going to explain how to transpile the temporal dead zone in AranLang. In JavaScript, a variable is set to be in the temporal dead zone when it is present in the environment, but has not yet been initialized. And accessing a variable in the temporal dead zone throws a reference error. Consider this JavaScript program. First, f is invoked. Reading x is currently forbidden because it has not yet been initialized. Then x is initialized, and it can now be accessed. F is invoked a second time, and it no longer throws a reference error. Note that the read within f was first forbidden and then permitted. So even if this code is very simple, it has quite a complex behavior. Let's see how to represent this behavior in AranLang. Variable declarations are explicitly hoisted at the beginning of the block. X is initialized with a specific symbol that indicates that it is in the dead zone. Then the initialization of the function is also hoisted. The unsafe access to x has been replaced by an explicit conditional expression. If the value of x is still the dead zone symbol, a reference error is thrown. Otherwise, the value of x is returned. Here, f is invoked normally. The initialization of x becomes a regular write. And here, the dead zone checked has been bypassed, which requires static analysis. Finally, f is invoked again normally. I want to make two remarks about this AranLang code. First, we can look at it as being a more explicit version of the original JavaScript code. Making explicit the implicit semantics of JavaScript is a recurring theme of my transpilation. Second, it will still resemble the original JavaScript code, and this protects the source adjacency of my framework. We can now move to how my framework instruments AranLang. Our experience shows that implementing an ad hoc EST visitor is already a valid strategy. But to be more expressive, my framework exposes an aspect-oriented API. As a reminder, an aspect implements a cross-cutting concern. It consists of an advice and a point cut. The advice is the cross-cutting logic, and the point cut dictates how to insert the advice at different points in the execution. This process is called weaving. I can now present the complete instrumentation pipeline of my framework. Here is the baseline execution of a program. My approach relies on source instrumentation. The user configures the instrumentation by providing an aspect. Its point cut defines where to insert the analysis logic, and its advice defines the analysis logic. Crucially, the point cuts act on AranLang rather than full JavaScript. So the boxes in blue represent the baseline execution. The boxes in dark red represent my framework. The boxes in light red represent data generated by my framework. And the boxes in yellow are the analysis, which is written by the user of my framework. I will now demonstrate how my framework simplifies tracing the call stack. The analysis modifies the baseline behavior of applying function. First, it logs the name of the function, the argument and the code location. Then it applies the function. Then it logs the result. And finally, it returns the result. Now, consider this baseline execution of the factorial function. To conduct the analysis, we tell Aran that we are interested in function applications. This results in a trace of the call stack. It precisely describes how the output 6 was computed. Note that we are able to record binary operations, although the analysis does not mention it. This is because Aran normalizes binary operations into regular function calls. This concretely shows how instrumenting AranLang is simpler than instrumenting JavaScript. This tracing analysis demonstrates the apply at around join point. But Aran exposes 31 join points in total. This is much more than what we could have with lambda calculus, but much less than what we should have with full JavaScript. They provide an interface capable of conducting shadow execution, which is one of the most demanding dynamic analysis techniques. In other words, supporting shadow execution ensures that my framework remains generic and applicable to many analyses. I conducted 2 experiments to evaluate the transparency of my framework. This first experiment evaluates its performance overhead on Octane. The experiment was conducted on Node.js and involved 3 analyses. The first analysis only applies AranLang normalization, and it already introduced a slowdown factors in the hundreds. So it seems that normalization is preventing Node.js from applying important optimizations. The second analysis specifies a complete point cut, but a minimal advice. So in other words, every single join point is being advised, but with simple forward logic. It introduces a slowdown factor that rarely exceeds 1000. The third analysis conducts shadow execution to record a dependency graph for every single value. It introduces a slowdown factor that can reach multiple thousands. The bottom line is that my framework has high performance overhead, and this means that it's not appropriate to analyze time-sensitive applications or program with heavy computations. The second experiment evaluates the semantic overhead of my framework on test 262. It is the official conformance test suite of ECMAScript and contains more than 90,000 test cases. The idea behind this experiment was to link semantic discrepancies with assertion failures. To diagnose those failures, the experiment was separated in multiple stages. The 2 first stages at the top only exercised the experiment setup without Aran. Most of the failures were because Node.js was lagging behind the specification. Then Aran normalization introduced 230 failures, and the 2 other analyses did not introduce additional failures. The bottom line is that my framework introduced very little semantic overhead, with a success rate of more than 99.7% on test 262. Here is how I categorize semantic discrepancies related to Aran. Each category corresponds to a JavaScript feature that AranLang struggles to cover. For instance, these discrepancies are caused by code verification. In JavaScript, it's possible to obtain the source code of a function. But after instrumentation, this source code is altered, which causes the discrepancy. This is a typical challenge of code instrumentation. In the first part, I have introduced my instrumentation framework. This framework is used in the second part to track the provenance of values. In this second part, we are focusing on the analysis that I code Provenance-Aware. Information flow is a typical example of such analysis. It involves detecting violation of security policies, such as a password should never be displayed on the screen. This requires tagging values with a sensitivity level. Other provenance-aware analyses are generation of test input to maximize coverage, tagging values with type information, or program slicing. So, while data provenance is conceptually simple, it serves as the basis for a wide range of advanced analysis. I will motivate my approach with an example analysis. The analysis is about detecting when values can be computed statically rather than during execution. The goal is to improve performance by computing these values ahead of time. This advice.pgs file describes how I would like to specify the analysis. Note that this comparison has 4 equal signs, which is not standard in JavaScript. It is a novel operator that I name provenential equality. I use this special .pgs extension for JavaScript files that can use this operator. First, I will create an array to mark values that can be evaluated statically. Then I will specify two functions in the advice. The first being primitive at after. It will mark the result as being static before returning it. The second being apply at around. It will first forward the function call. Then it will check whether all the inputs are static. If this is the case, then the output can be reported as candidate for ahead of time evaluation. We also mark the output as being static to transitively detect candidates. And finally, we return the output. For instance, on this simple program, the addition at line 1 should be reported as static. If we would have replaced provenance equality with regular JavaScript equality, the analysis would not be able to differentiate the 42 that has been statically computed from a user input that happens to also be 42. As a result, the multiplication at line 3 would also have been reported as static, which is incorrect. Let's better identify how we would like provenance equality to behave. Here, the value that we want to track is the number 42. We want to track provenance through the environment so that num is provenentially equal to itself, but not to the same number that originates from another literal. We also want to track provenance through function calls. So for instance, the result of the identity function should have the same provenance as its argument. We also want to track provenance through objects, and provided the tracking above, we should be able to track provenance through method invocations as well, which is how provenance equality appeared in the example analysis. Most managed languages already provide true comparisons: referential equality and structural equality. Structural equality compares value based on their content, while referential equality is stricter and typically compares composite values based on their provenance. I introduce provenance equality as a third comparison that is even stricter than referential equality. It compares both primitive and composite values based on their provenance. To precisely understand the research question of this second part, we need to consider three different executions of the same program. The first execution uses a regular allocation system where primitive data are inlined into values. This is a very common optimization. First, 42 is assigned to x, then 42 is assigned to y, and finally the object is allocated and the new address is assigned to z. The issue with this allocation system is that these three 42 values share the same exact identity, which prevents implementing provenance equality. The second execution uses another allocation system that preserves provenance. In this allocation system, values are always addresses for locations in the store. First, 42 is allocated and the new address is assigned to x. Then 42 is allocated a second time and the new address is assigned to y. Finally, the object is allocated and the new address is assigned to z. Within this second allocation system, the identity of primitive values has been refined, and provenance equality becomes straightforward to implement. Unfortunately, it requires a custom interpreter which is not portable. To preserve portability, we must rely on source instrumentation. That is that we must somehow approximate the behavior of the second allocation system within the first allocation system. The approach that I use is to replace primitive values with handle objects. First, a handle is created and the new address is assigned to x. Then a second handle is created and the new address is assigned to y. And finally, the object is allocated and the new address is assigned to z. In this third execution, the identity of values as defined by the second allocation system has been successfully recovered. But in general, this may not always be the case, and we must decide whether to make the approximation unsound or incomplete. In my work, I have chosen sound provenance tracking. That is that when I say that two values are provenentially equal, they actually are. So the research question of the second part is about defining this program transformation. In the next 3 slides, I'm going to explain some of the details of this code transformation. In this slide, I provide a minimal transformation for tracking provenance through the environment. The transformation handles 3 concerns. First is the promotion of baseline values into handles. The goal here is to make our approximation of provenance equality more accurate. Then is the demotion of handles into baseline values. The goal here is to preserve semantic transparency. Finally is the replacement of provincial equality with referential equality on handles. Note that we should not confuse baseline values and handles. Handles should never be promoted, and baseline values should never be demoted. This kind of separation between values has been studied in the field of security with access control systems. Consider this basic case. We start with a file that should be executed in a provenance-aware manner. This file is importing a third-party library where provenance should not be tracked. Note that after instrumentation, the code should still import the library, of course. Let's explore how this setup should partition value locations in the runtime state. To preserve transparency, the state locations associated to the library file should only contain baseline values. We refer to this location as the external region. To track provenance, the state locations associated to the original file should only contain handles. We refer to this location as the internal region. In my dissertation, I have explored how extending the internal region makes provenance tracking more precise. Finally, the transformed code is adding state location as well that can contain a mix of baseline and handle values. We refer to this location as the bridge region. I now want to focus on the presence of handles within objects. The goal is to improve tracking accuracy while remaining transparent. The program that requires provenance tracking creates a user. Then it ensures that the provenance of the age of the user is preserved. And finally, it logs the serialization of the user. In this example, the definition of provenance-related functions are in a separate file. The virtualized function uses the proxy API to give the illusion that an object is containing baseline values, whereas it actually contains handles. We can transform the target file and import these provenance-related functions. As before, we promote the result of evaluating 42. We create the user object, which contains the age handle. We virtualize it into an object that appears as if it is containing the number 42. We use the identity of handles to approximate provincial equality, and we pass the virtual object to json.stringify to preserve transparency. We have implemented our approach into a library called linveil. Linveil can be used within two architectures. The first is called advice layering, and I'm going to describe it through our motivating analysis. The advice being provenance-aware, it should be transformed by linveil, and after instrumentation, it imports the linveil runtime. But this is only half of the picture. The second half concerns the target of the analysis. To track provenance through the target, it should be transformed by linveil as well. But we still need to weave the advice of the provenance-aware analysis, and this requires a second transformation pass. We call this architecture advice layering, because it layers the advice from linveil, which tracks provenance, with the advice from the user, which is specific to the analysis. This architecture directly solves our motivating analysis and greatly simplifies the implementation of provenance-aware analysis. However, it requires two transformation passes, which causes heavy performance overhead. The second architecture reduces performance overhead at the price of simplicity. The target program still requires instrumentation to track provenance. However, now both transformations have been combined into one, which is more performant. Here is how we should adapt our motivating analysis for this second architecture. First, we need to provide linveil's advice as basis for the analysis advice. Then we need to explicitly promote the result of primitive literals into handle. We also need to demote handles before logging to preserve transparency. And finally, we have to replace reflect.apply with a function from linveil runtime. This second architecture is called advice extension because it relies on extending the advice from linveil with analysis logic. In this architecture, the advice is in the bridge region rather than the internal region. And this requires the user to manipulate a mix of handles and baseline values. In our experience, this is error-prone and hard to debug, which is where the simplicity penalty comes from. To evaluate the performance overhead, I deployed linveil on the Octane benchmark, as I did for Aran alone. There are 4 participating analyses. Aran normalization has been kept for comparison. Then is an analysis that only tracks provenance but without any additional logic. It already introduces a slowdown factors in the 1000. Then is an analysis that conducts symbolic execution with the advice extension architecture. It was not significantly slower than provenance tracking alone. Then is the same symbolic execution analysis, but with the advice layering architecture. It introduces slowdown factors in the hundreds of thousands. This gives a perspective of what the user has to pay for being completely protected from the complexity of tracking provenance. To evaluate the semantic transparency, I deployed linveil on test 262, similar to what I did for Aran. The same analysis participated in the experiment, and they all introduced the same semantic discrepancies. For instance, these discrepancies were because proxies prevent detecting cycles in the prototype chain. The bottom line is that linveil is highly semantically transparent, with a failure rate of less than 0.1% on test 262. In the second part, I have introduced my approach to track provenance, which is implemented on top of the instrumentation framework from the first part. Regardless of provenance tracking, analysis requires manual effort to be deployed on distributed applications. In this third part, I'm experimenting with alleviating this manual effort and automatically lift analysis to distribution. To motivate my approach, I'm reusing the same analysis from part 2, which was about detecting candidates for ahead-of-time evaluation. Consider this minimal distributed application. The server is registering a remote procedure, which is the identity function, while the client is calling this remote procedure with 42. And it increments the result by 1. If we consider this application as a whole, this increment operation can actually be conducted ahead of time, and we would like our approach to enable this detection. A first attempt will be to duplicate the analysis on the client and the server. In this setup, both the client and the server has been instrumented, and the advice is running independently in both processes. After loading the advice, both processes have allocated their array for registering static values. First, the client evaluates 42, which is registered as being static. Then the client calls the identity function on the server, and the server responds with the same value. Because the client cannot be sure that the result shares the same provenance as the argument, it promotes it into a new handle. Then the client evaluates 1, and the increment operation is performed. Because we could not track the provenance of 42 across processes, the analysis did not report that 43 could have been evaluated ahead of time. This demonstrates that the analysis requires orchestration to reason about the distributed application as a whole. It is possible to modify the advice to perform orchestration, but it requires manual effort. My approach is to execute the advice from the user in a separate process. In this second setup, there is still an advice present on the client and the server, but it is no longer written by the user. Now, there is only one array of static values, which is located in the analysis process. After evaluating 42, the client requests the analysis to advise the primitive at after join point. The analysis allocates a handle, registers it as static, and returns its address. Then the client calls the identity function, which is located on the server. Note that it sends a handle address rather than the number 42. And the server responds with the same address. After evaluating 1, the client requests the analysis to advise a second primitive at after join point. Again, the analysis allocates a handle, registers it as static, and returns its address. Then the client is evaluating the increment operation, and it requires the analysis to advise the apply at around join point. Because the addition function is located on the client, the analysis responds with a loopback request to forward the application. The client responds with 43, and the analysis returns a handle address for that value. Because all the inputs were registered as static, 43 was marked as a candidate for ahead-of-time evaluation. The challenge with this communication is that the increment operation is synchronous, yet the client should remain responsive to loopback requests from the analysis. To solve this issue, I came up with a protocol to call remote procedure synchronously, but in a responsive manner. Synchronous yet responsive remote procedure calls is not enough to implement my approach. The other requirement is for the advice to manipulate references to remote objects as if they were regular references. Otherwise, we would let the complexity of distribution creep back into the analysis specification. To implement these isomorphic remote references, we leverage the proxy API a second time. To illustrate them, I will now explore how they interact with linveil's own virtual values. So handles are created by the analysis process, and they are made available as remote references to the process under analysis. These remote handles can be embedded in objects. But these embedded handles must be concealed from non-instrumented code. And we achieve this by providing a remote reference to an linveil proxy. So as we can see, a simple property access may involve up until 3 sequential hops. This is obviously very inefficient and introduces a lot of performance overhead. This is the price that the user has to pay to be completely protected from the complexity of distribution. With lifting analysis to distribution, I pushed my framework to the limit. The heavy performance overhead makes it impractical to use this approach on real-world applications. However, it has shown merits for prototyping and demonstrations. As validation, I lifted Symbolic execution on a demonstrator app for the socket.io communication library. This simple app is a collaborative drawing application where multiple users can share the same canvas. The lifted analysis was able to reconstruct a computation tree that spans across multiple processes. I have now finished presenting the 3 main parts of my PhD, and I will conclude this presentation. During my research, I have implemented numerous tools, and they have been used internally at Soft. They were the basis of many bachelor and master theses, and even 2 PhDs. I also engage with my users worldwide. My flagship project is Aran. It is by far the largest codebase, and it required a lot of engineering effort. This is because it has to deal with all the corner cases of JavaScript. Linveil also required significant engineering effort, but the difficulty was more about properly handling reflection. I am now going to wrap up this presentation with a short summary. We started with the background where we introduced source code instrumentation. We stated that it should be transparent and that it has several key strengths. It is portable across language runtimes. It is generic and applicable to a wide range of analysis, and it provides insights that are adjacent to the source. The main drawback is that it is complex and requires a lot of manual effort. The 3 main parts of this presentation are about simplifying source instrumentation while protecting its strength. In the first part, I introduced Aran to facilitate instrumentation. It involves instrumenting a minimal variant rather than the full source language. I was able to achieve a very high level of semantic transparency, but it comes at the price of some performance overhead. Also, it's not completely adjacent to the source anymore. In the second part, I introduced linveil to track the provenance of values. It involves promoting values into handles that can be tracked. It greatly helps to express provenance-aware analysis, but it comes at the cost of additional performance overhead, especially for the advanced layering architecture. Finally, in the third part, I introduced Aran Remote to lift analysis to distribution for free. It involves executing the analysis in a separate process. It completely protects the user from the complexity of distribution, but it comes at the price of heavy performance overhead. Thank you for your attention.